All right, so just as a quick review, let's go ahead and do this problem that I gave you guys last time, just to make sure that you feel comfortable with these. So I'm going to start with the ratio test again. So I need the limit as n approaches infinity, absolute value, 3x minus 1 to the n plus 1. This is going to be the cubed root of n plus 1. Then I'm going to multiply by the reciprocal of a sub n, which would be that. And my goal is for all of this to be less than 1. So if I were to break apart this 3x minus 1 to the n times 3x minus 1 to the first power, the ones that are to the nth power would cancel. And then I'm going to put the cubed roots together. Like so. The n's have no way of being negative because they run from 1 to infinity. So I'm going to take this 3x minus 1, leave it in the absolute value, and pull it out in front. And then in here, I am going to rewrite this by dividing everything by n. So now when I take the limit, this guy will go to 0, and that whole limit will go to 1. So then I have 3x minus 1 absolute value times 1 must all be less than 1. Or that must fall between 1 and negative 1. So I'm going to add 1 everywhere. And divide by 3 everywhere. So 0 less than x less than 2/3. So this is my interval. My computer, what are you doing? There we go. And I need to test the endpoints. So left endpoint means I plug 0 into the original summation. So that would be 3 times 0 minus 1 to the n all over the cubed root of n. So that's going to be some 1 to infinity of negative 1 to the n over the third root of n. That's an alternating series. And so I need to prove that it's decreasing. So I would plot the absolute value. So let me see what that would look like. Of course, I got to put it in the right form first. There we go. So graphing that, it looks something like this. So that is decreasing. And then the second part is this guy going to 0 and we take the limit as n approaches infinity of the absolute value. So that would be just 1 over the cubed root of n. That very easily goes to 0. If it meets both criteria, this converges for alternating series, which means we're going to include 0. And then let's just repeat for the right side. So we start with the original summation, plug into thirds. That's going to simplify. Excuse me. So the 3's would cancel. And then you'll have 2 minus 1 to the n. So you just get 1 to the n, or 1, over the cubed root of n. That can be rewritten as 1 over n to the 1/3. That's a p series. P equals 1/3, less than 1 means diverges, which means we do not include the right endpoint. What's that?
Does it change if it's 1 to the nth?
You mean if you wrote it like this?
Like in the numerator? Yeah. Is it? Why wouldn't the n be there?
Well, it is 1 to the n, but remember that 1 to any power we can just write as 1.
Okay, yeah.
So we can kind of interchange both of those. So that one diverges, and therefore our interval would be this. So hopefully you guys got that yesterday. So let's go ahead and jump into the new stuff here. So Taylor and MaClaurin series. So you may have noticed last time when I was talking about power series, I mentioned transcendental functions, and those are things like e to the x, natural log x, cosine x, stuff like that. Come on. And these functions cause some trouble when we start to do things like take derivatives, integrate, and solve differential equations. So there was a way devised that we could rewrite them or represent them as a power series. So an example here for e to the x, the power series is x to the n over n factorial. And if you start expanding the series or writing out the first few terms, it is nothing more than a polynomial. And that's really great because polynomials are really easy to work with. Right? Derivatives, integrals, all very easy for things that are x to the 5th or x to the 1/2, things like that. So first, let's prove that this representation, this summation here, is a good approximation to e, or e to the x. So it says, let's consider e to the 2nd power, and let's prove that this sum works for that. So first, could someone put e to the second power in their calculator and tell me what that is, excuse me, to 5 decimal places?
$7.38905.
7 point.
Rounding up would be the 6. So 7.38906.
All right, thank you. All right. Part B says, write the first 7 terms of the power series. Okay, so that's the sum starting at 0 to infinity of x to the n over n factorial. So first plug in 0, so x to the 0 over 0 factorial, plus plug in 1, x to the first over 1 factorial, then plug in 2, and so on. We do this to 7 terms. So that's our first 7 terms. Then it says, okay, now substitute x equals 2 into that polynomial and then approximate the number. So first, let's rewrite this. X to the 0 is 1, and so is 0 factorial. So I don't think that we went over that when we reviewed factorials. And I don't remember the proof off the top of my head. But in order for the definition of factorial to work, 0 factorial has to be 1. So this whole first term is just 1. Then this next term is x to the first over 1 factorial. That's just x. Then x squared over 2 factorial is x squared over 2. Then we have x cubed over 6. This is x to the 4th. That's 24. Yeah. And x to the 5th. I think that's 120. Let me check myself. Remember, you can go to math, go to the PRB menu for probability, and option 4 is the factorial. And then finally, this is over 720. So now part C says plug 2 in there. So 2, this is going to be 2 squared over 2, 2 cubed over 6, 2 to the 4th over 24, 2 to the 5th over 120, and 2 to the 6th over 720. So if someone would be kind enough to go ahead and calculate that for us, I will start to work on it myself here.
I got 7.35 repeating. Like the 5 is repeating, but I also did it a little quickly, so there might be some error there.
Can you say that again? Sorry.
7.3 and then 5 repeating.
And just a bunch of 5s.
Yeah.
Okay. Let's just see what I get here real quick. So yeah, I got the same thing. So now they want us to compare this to the actual thing. So here is one downfall of a power series. We took 7 terms, right? That only gave us up to 1 decimal place accuracy. If we took 1 more, we might be pretty close. Let's see if we add 2 to the 7th divided by 7 factorial. That's 7.3809. So that's much closer. 1 more term would probably get us as close as we might get with 5 decimal places. So you got to take a lot of terms, is what I'm trying to say. But it is valid, right? It is pretty close to the number that was given, and it was just a simple polynomial. So I'm actually going to skip ahead and do MaClaurin first. It's much easier, and the Taylor series is kind of what I would like to call a MaClaurin shifted. So I'm going to skip ahead to the MaClaurin first. And I think it relates a little bit better. So what we just tested was a power series representation for e to the x. The way that we solve for that power series representation is to create what's called a MaClaurin series. Now, don't be alarmed by the fact that it says it's a specific Taylor, because we haven't done that yet. But most importantly, it's centered about 0, which means that if you look at the formula here, you plug in 0 everywhere, which is really nice, right? 0 is a great number to work with. So the left-hand side is the closed formula or closed form. The right-hand side is the first couple terms multiplied or written out and added together. So the form there, it's a summation starting at 0 and running to infinity. This f of n in parentheses is the nth derivative of the function evaluated at 0 over n factorial and times x to the power n. So let's just look and see how they get these first couple terms. The first term is when n is 0. So the nth derivative, right, f of 0, is really just the function, the original function, right? If you don't take a derivative, then you're starting with the original function. So that's how they get f of 0. Then you'd have x to the 0, and you'd have over 0 factorial. But of course, we know x to the 0 is 1. 0 factorial is 1. So the first term is just f of 0. The next term is when n equals 1. Right, so this was n equals 0, n equal 1. So this would be the first derivative evaluated at 0 divided by 1 factorial times x to the first. That's that term. And you just keep going up from there. So how do we actually use this form? Well, we start with a function, and we're asked to create the power series for it. So here's a function, f of x equals e to the minus 5x. So in order to write out the terms, I need the derivatives. So I need f prime. I need f double prime, triple prime. Let's see if 4 is enough. Now it says use the first 20 terms. So you and I are not going to write out all 20 terms, but we can use a program to do that for us. We can just write out the first 4 or so, just to get the idea. So f prime is going to be minus 5 e to the minus 5x. Right, it's exponential. You just bring the minus 5 down each time. So the next one's going to be 25 e to the minus 5x. Then minus 125. And then finally 625. And of course, this continues on. Then we need these evaluated at 0. So I need f of 0, f prime at 0, and so on. So the original function, right, e to the minus 5 times 0. That's going to be e to the 0 or 1. So each one of these, the exponential is just going to go to 1. So basically, we just get the coefficients. Everybody with me so far? All right, no peeps, no thumbs up. I'll take that as you're either completely screwed or just following along. Let's hope the second.
So because we made we're replacing the x with a 0, that gets rid of like the negative 5x and so on, with the exponent at least.
E to the minus 5 times 0 equals 1. So for every one of those terms, this goes to 1.
Okay, so and that just makes it itself. I gotcha.
And you just get the coefficients.
Mm-hmm. Sounds good.
Okay. So now let's use the form. So it says, and let's go ahead and just use this side for now. The first term is just the function evaluated at 0. So e to the minus 5x is approximated by 1 plus, right, because f of 0 is 1. F prime of 0 is actually minus 5 divided by 1 factorial times x to the first power. The next term is f double prime, which is 25, divided by 2 factorial and times x squared. The next term is minus 125 times x cubed over 3 factorial. Excuse me. And finally, we would have plus 625 x to the 4th all over 4 factorial. And then I'm just going to put plus dot 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 because we're asked to do the first 20 terms. Now, before I continue, if I'm expected to get the first 20 terms, well, then I have to be able to give the program some way of determining what those first 20 terms are. So I want to rewrite these in a closed form. So we need to find a pattern. Does anybody see a pattern that these terms follow?
So they're all being multiplied by 5, and the exponents are like increasing by 1 each time. Or I'm sorry, not the exponent, the number in the denominator. So you could do something. So it'd be like you'll multiply it by 5, and I'm not quite sure what you do for the denominator, other than like I guess just add 1 to the denominator.
All right, so it looks like this is 5 to the first, x to the first over 1 factorial, right? 25 is 5 squared. Then we have x squared over 2 factorial. Now, are you starting to see the pattern?
Mm-hmm.
So you're on the right track. We just have to rewrite them. And of course, this first term, 1, we can write as 5 to the 0, x to the 0 over 0 factorial, right? So if I look at this, it looks like 5 times x to the power n, if n starts at 0, then it's divided by n factorial, and let's see, we're alternating as well, right? We start at a positive, then negative, positive, negative. So it looks like it's negative 1 to the n. Right, negative 1 to the 0 power is positive 1. Negative 1 to the first power, which would be that term, is negative. So all the odds are negative. And which that means we can just, because it's power n as well, throw it in there. So this is the power series representation for e to the minus 5x. You may notice that if I were to go back up here, when we did the e to the x earlier, it was x to the n over n factorial. And now we're doing e to the minus 5x, so it became minus 5x to the n over n factorial. All right, so you're probably sitting there going, okay, great, you're talking a lot, you're making stuff up. What good is this? So again, the problem asks us to use the first 20 terms. This is my function. So I'm going to do this two ways. I'm going to have you do it on your calculator. Notice it says use the first 20 terms to approximate e to the minus 15. Okay. So what I want you to do is for e to the minus 5x to look like e to the minus 15, you'd have to plug in x equal 3. So if we just do that down here, right, e to the minus 15 would look like that. And you can input this into your calculator. So you're going to go again to math, go over to the fourth option, which is PRB, or hold on. Sorry, under the math tab, and then the first option should be, for me, it's option 10. It's called summation. And it comes up really nicely. So I want you to go ahead and calculate that. And while you're doing that, I am going to plot this function so we can see when it's good to use this approximation and when it's not. All right.
So instead of it being e to 15, wouldn't it be e negative 5 times 15? Wouldn't the 15 only cancel the x or substitute for the x?
No, you're trying to make the whole exponent be negative 15, and it was already minus 5x. So you're letting x equal 3.
Oh, so that's only for the third term? Or would that represent the 15th term?
No, this x is not the term. X is going to be the thing we're plugging in for here. N
Oh, okay.
represents the number of terms.
Okay, I gotcha.
So was anybody able to get a number there? Now, of course, sorry, I forgot to point out, you obviously don't want to run to infinity. Your calculator is going to cry. Right, it asked us to use the first 20 terms. So actually you'd run to 19 technically. right? You're starting at 0. Let me see what I get here. So I get negative 7,900 or 79,065, something like that. For the summation.
Yeah, that's right.
Okay. What did you guys calculate e to the minus 15? Just see what that would actually be. Not even close, right? So the question is why? Why are we not getting a good approximation? So let me show you my plot here and see if this helps. So what I've done is, let me actually take the to 19. So I've taken the first 20 terms of e to the minus 5x, and you'll notice the first 5 here are the ones that we calculated together. So I took those and I plotted them along with e to the minus 5x. So let me get rid of the approximation first. So that's what e to the minus 5x looks like. Okay, right, it's an exponential, it's negative, so it starts up high and then it decreases. And notice it falls off. So out here at 3, right, it's some really small number, right, close to 0, which we calculated was 3 times 10 to the minus 7. Now, if I reintroduce the function that we calculated, it looks great on this end. It overlaps the other function. And it's pretty good, maybe up till about 1. And then if we were to zoom in here, these start separating. You can see definitely after 1.5, they've already separated. And notice this function now just starts going off towards negative infinity. So by the time we get to 3, right, it doesn't even show us how far off we are. Here we go. So here's 3. This thing shot off God knows where. So there's e to the negative 5x, and this is our approximation to it. So basically what I'm saying here is using 19 terms of that series is only good for x from, you know, the negative values up until about 1 or 1.5. Any number bigger for x, this doesn't work very well. So now the question is, how many terms do we need? I think, I want to say it's like 50 some. So there's all those terms, right? They're really disgusting. Let me come down here. So notice I've plotted 56 terms or 57 terms, and this is still, the approximation is still only good until about 3.8, and they start separating. So if we wanted to get that number exactly, right, we'd need to put in 50 some terms. Oops. So what I'd like you guys to do is to go in your calculator and see if it'll handle it. See if we can do 50 terms, if that'll match up now. That should give it to us. So go to your calculator and do that summation. But I want, instead of 19 terms, choose, say, 49 terms. Let's try that. So even then, it's not very good. Let's try the 50 some that I had before. All right, if you do 54 terms, you get 3.03 10 to the minus 7. So 55 terms are required to get a good approximation. So this is a really good demonstration as to when do these things come into play. So you may have heard me at one point talk about a differential equation from physics, and we take sine of theta and we say, well, if theta is small, we can say sine of theta equals theta. Well, that's the same thing here, right? We say if x is small, well, then we can approximate this by maybe the first 5 terms. And by small, we mean close to 1 or 0. Okay. So any questions so far? I know I did a lot of stuff there about the MaClaurin series, what it is, how you calculate it, what it's good for, any of that stuff. You guys already hate it?
So if we had this on an exam and like, you know how you were testing like the amount of terms we needed and everything to get it closer to the closest to like the actual answer, but would you have to do that? And if so, like, how do you determine testing for that? Do you just like put in random numbers or just like?
I don't think that I would ask you how many terms is required to get a good approximation.
So if it ended and it wasn't a good approximation, like with the negative, the 79,000, like we could leave it there.
Yep.
Okay, thank you.
What do we plug into the calculator? So I did the, you're probably doing some formatting, is my guess. You can see that guy there. So I made sure to put the negative 15 in parentheses to the x power, and then I did x factorial inside parentheses as well. And then I ran from 0 to 54. And that gave me 3 10 to the minus 7. All right. No problem. So I think there's one more of these. So I want to go back now and do the Taylor series. I'm going to go ahead and do the cosine one here. So let me actually copy this to that page. So recall that in the notes it said that the MaClaurin was a special Taylor series where A was equal to 0. So hopefully you can see that if we made A 0 here in this form, it would collapse down to what we used for the MaClaurin. So the only difference here is instead of plugging in 0, we're plugging in whatever the value of A is. And then we are, instead of putting X, it's X minus A to the N. That is the only difference between the MaClaurin and the Taylor. So again, we need to take our derivatives. So f of x is cosine f prime. It's going to be minus sine double prime minus cosine triple prime back to sine. Fourth derivative is going to be cosine again. And I think we're going to need maybe 2 more. Let's see. And the reason I say that is because I want to always have, at the very least, 3 to 4 terms that I get out of these. So those are all my derivatives. I'm now going to apply f at A. So cosine of pi is going to give us what?
-1.
Thank you. All right, sine of pi, 0. Negative cosine pi would be 1. Sine of pi is 0. Cosine pi is -1. 0 and 1. Okay. So now I need to take these and plug them into the form above. So my approximation is f evaluated at A, that's -1, plus, and here's where a lot of people go wrong. They'll go, oh, look, this is 0. I don't use it. I'm just going to jump to the next one. But instead, you first have to include those terms that are 0. So f prime, right, is the next term. So it's 0 over 1 factorial times x minus pi. Then the next term is f double prime, that's 1 over 2 factorial x minus pi squared. Just continue down to the next line here. 0 over 3 factorial x minus pi cubed. Then looks like a -1 x minus pi to the 4th for 4 factorial. Oops. Okay, so -1, 0, and then 1. All right. There we go. 1, 2, 3, 4, 5, 6, 7. All right. Then this term, and this term all disappear. So I'm left with -1 plus x minus pi squared over 2 factorial minus x minus pi over 4 factorial and plus x minus pi to the 6th over 6 factorial. So now the question is, can I write this in a nice closed form? So this would be continuing on. So any patterns that you recognize? Please, not everybody at once.
So if -1 is the like term when n equals 0, could we consider like where there's a 2 and 2 factorial and then 4 and 4 factorial 2n?
So yeah, every one of the denominators is even, right? And we represent even numbers by 2 times some variable. So we could do 2n factorial as long as we start n at 0. Right? Because 2 times 0 is 0. 0 factorial is 1. That works for the first term. When n is 1, 2 times 1 is 2 factorial. That's what we have there. N is 2, we get 4 factorial. So they match up. Okay. What else do we see? How about the x minus pi's? Aren't they going up by the same power? Right, so there was 2 factorial, 4 factorial, and it was second power, fourth power, sixth power. So it's also to the 2n.
And then it's like oscillating between adding and subtracting. So where would you put the negative? Because if you put a negative, then you just, would you put the negative outside?
You can put one by itself. It doesn't have to go inside. And we have to start with a negative, right? So if we try to do -1 to the n, that won't work because -1 to the 0 is +1, and we start with a negative. So we could do n plus 1. And that'll give us the correct sign each time. So that is our closed form. So any questions about that Taylor series? Do you guys think you're ready to go ahead and try the two that are left. There's one MaClaurin here, sine of 2x, and then the Taylor above, which was e to the x expanded about a equal 3. Yes, no, maybe, we don't care. Hey, I see a thumbs up. All right.
Thank you.
Thank you. So let's see. Guys, we're talking about this one, right? Oh, wait, maybe I'm not sharing that screen. Hold on. Shoot. This problem?
Yes.
That encroached on everything. Second. What in the world? Come on now. Sorry, I'm just trying to clean this up real quickly. It's not working the way I would hoped. Come on. There. Ooh. Okay. All right, so f of x is sine 2x, so you need to take your derivatives. Okay. Then we need all of them evaluated at 0 because we're doing MaClaurin. So any of them that are sine, if I plug 0 into sine, I get 0. So those are all 0. And the cosine of 0 is 1. So I just get the number in front. So then if I write out the first couple terms, then I've got 0 plus 2 times x to the first over 1 factorial plus 0x squared over 2 factorial plus a negative 8x cubed over 3 factorial plus 0x to the fourth over 4 factorial plus 32x to the 5th over 5 factorial. Good with that so far?
Yes.
Okay. And then if we simplify that, right, getting rid of all of these 0 terms, which you don't want to do too soon. And then to help us see a pattern, I will write it this way. And of course, this is all continuing on. So if I look at that, looks like I have a power of 2, a power of x, and they go up 1, 3, 5. So they're going up by odd numbers, which you represent as 2n plus 1. The denominator does the same thing. It's 1, 3, 5. They're all odds. It's 2n plus 1 factorial. And then it alternates from positive, negative, positive, and then the next one would be negative. So negative 1 to the n, starting at 0. Don't always have to start at 0. Doesn't always have to be n power.
How would you put that in your calculator?
What are you trying to calculate?
Like, to compare like the numbers that you get?
So you're trying to do the sine of 10?
Well, wouldn't you have to put that in your calculator too?
Right, but so this is an approximation for sine of 2x.
Oh, okay.
So if you want to do sine of 10, right? Well, then instead of 2x,
yeah,
you plug in 10.
Okay, gotcha. Thank you.
And then, of course, don't try to get your calculator to run to infinity. It'll cry. All right. Well, just let me scroll. All right. So are we good with that before I continue?
Yes, thank you.
So I think the last thing I'm going to do today potentially is this. I may get an example done of the next section. Of course, we will finish that up tomorrow and review tomorrow as we have our test coming up, unfortunately, already on Tuesday. So let's go ahead and get this guy in here. I just put up the power series, common power series on Blackboard. So there's a Word document that's got common power series there. However, for this first one, this power series is different. It's just here to really drive home the point. So all this time today we've spent finding power series representations. What good are they? Well, I keep saying that we're going to use them, right? So it says here's a function now that's x squared times e to the x. Well, we know that power series are represented by polynomial functions. So I'm going to leave the x squared alone, and I'm going to use the power series representation for e to the x, and I'm going to multiply those two together. So this x squared has no n's in it, which means it can go in and out of that summation freely. So if I take it in, I can rewrite it this way. So in fact, you could rewrite x squared e to the x as this summation. And so if I were to write out, say, the first 5 terms of that sum, that would be an approximation to this equation. So first we have to learn how to do that. Then we can start to use that information to integrate and differentiate and take limits. So these exercises just ask us to take these functions. I guess there isn't nothing on the last page. And transform them into sums. So anytime we see a polynomial, we're going to leave it alone. So here I've got x cubed. So I'm not going to touch that. I instead want to replace this function. And my guess is that many of you have never seen this function. It is called the hyperbolic cosine, or sometimes referred to as cosh. And I'm not going to go too into detail into it. But it's a function that you'll see later on in your, as we always say, college career. Now its power series representation is sum x to the 2n. I think it's 2n factorial. Let me just check. Yep. And from 0 to infinity. So again, this is a great example because, for one thing, we have no idea what this cosh function is. But if we use the power series, we could create a polynomial function to represent it. So f of x is now going to equal x cubed times this power series representation for cosh. And again, x cubed has nothing to do with n, so it can come inside the sum. And x cubed times x to the 2n, you just add exponents because they are the same base. That's the power series representation for that function. So just for the experience, let's see what the first couple terms look like. Let n equal 0. I'm going to get x cubed over 0 factorial, so just x cubed. If I let n equal 1, I'm going to get x to the 5th over 2, right? 2 times 1 is 2, 2 factorial is 2. And let's just go one more. If I let n equal 2, then I have x to the 7. And what's that, 24? Okay, so that would then be what we could plug in instead of x cubed times the hyperbolic cosine. So I think maybe I'll do B. I'll let you guys try C, and then I might go ahead and start one or two problems from the next section. So B, I want to rewrite it just so it's clear that this is x times 1 over 1 plus x.
Can you scroll up a little real quick just so I could take a photo of the first problem? Thank you.
So I'm going to go to my common power series sheet here and see if we have that one. So notice down here I have 1 over 1 plus x. is equal to the sum from 0 to infinity of -1 to the n, x to the n. So let's go back to our sheet. And I'm going to replace 1 over 1 plus x with the sum n equals 0 to infinity, -1 to the n, x to the n. Again, this x can go inside, and we'd be multiplying x times x to the n, which is just going to be x to the n plus 1. So that's our representation. So this isn't difficult. It's just a matter of finding it in the table and using the proper pieces. And I guess knowing which ones to plug in for. So let me just pull up the next guided notes. I'm going to skip ahead here because I really just want to get to the meat of what we're doing. So I'm going to skip this guy. I'm going to jump right to here. So everything we've done today has led up to this. Here's an integral, 1 over 1 plus x to the 4th dx from 0 to 0.4. We learned a bunch of integration techniques at the beginning of this course. So this could be done using what method that you recall?
Partial dissociation.
I
Partial
think
fraction.
you could do partial fraction. Another option I think would be, and again you have an addition of 2 perfect squares, so that would be kind of hard, right? If you try to factor that, you'd get complex numbers.
Yeah.
So I think actually a trig substitution would probably be best. But those can be quite tedious. So instead, let's go ahead and try to use the power series. So it says use the first 6 terms of the series 1 over 1 plus x. But we've got 1 over 1 plus x to the 4th. Well, remember that earlier we had e to the x was x to the n over n factorial. And then we went ahead and did e to the minus 5x. And it just became minus 5x to the n over n factorial. So it was like we just replaced the x, right? Well, if we've got 1 over 1 plus x and we need x to the 4th, well, let's just slap x to the 4th there and x to the 4th there. That then is x to the 4n. It says use the first 6 terms. So let's take the first 6. So that's going to be 0, 1, 2, 3, 4, 5. So when n is 0, and then n is 1, and so on. So simplify that. This first term is all going to be 1. And we're going to get minus x to the 4th plus x to the 8th minus x to the 12th plus x to the 16th minus x to the 20th. So that is the first 6 terms of the power series expansion of 1 over 1 plus x to the 4th. I would then plug that into the integral. Now here's where it turns out to be really nice for us, right? Because integrating polynomials is really simple. This is just going to be x minus x to the 5th over 5 plus x to the 9 over 9 minus x to the 13 over 13 and so on. And then all evaluated from 0 to 0.4. So you just got to plug 0.4 in everywhere. This is probably the hardest part of the problem, is plugging it into the calculator at this point. And let's see what that comes out as. And if you beat me to it, let me know what you get. Unless you're just all sitting there waiting on me to do it. If you have a question, let me know. All right, if I did that all correctly, I get 39798. Just the 5 decimal places. And then, of course, we can use the FNINT function. which hopefully you remember is under the Math tab, number 9 option. And it comes out exactly the same. So we only used 6 terms, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out the 10 decimal places, it's accurate. Now, of course, again, remember I said that this works well when x is small. And if you look at the integral, it went from 0 to 0.4. Those are small values. So that's why only 6 terms were needed to get such accuracy. So I think maybe I'll let you guys try the other one here. And then I think we'll call, we've only got about 15 minutes, so I'll just do that for today. We'll finish up the next section next class. Sound good to you? Guys, just want class to be over with today, I'm guessing.